Hello and welcome into this analog synthesizer circuit analysis tutorial. As a study case, we'll be taking Soundlab Ultimate Analog Synthesizer designed by Ray Wilson. I think almost exactly 10 years ago. So this is a tribute to Ray Wilson. Now, this on the picture here is actually the synthesizer that I myself have assembled based on this open source design that you can find in here. It's called musicfromouterspace.com, and we can actually go to that website right now, and I'll show you what it is. So this is Ray Wilson, a really amazing engineer. So if you go to Synth DIY, this on the right hand side, all of these are his DIY analog synthesizer projects. So look at the vast, just sheer amount of work. So all of these kind of chapters here, you can expand it, and it has information starting from basic theory behind how the so in this case, what is it, digital to analog converter, how the circuitry works. So let's open the VCO, the one that I'll be talking about. This is voltage controlled oscillator. So everything starting from the design of the circuitry, some explanation of how that works, the PCB designs, tips and tricks, and so on. And like this, he has material for all of these I don't know how it's called, a chapter probably. So very, very amazing. And we will take that as a study case and explore how, just exactly how the analog synthesizers work. And in this specific tutorial, we'll be only talking about a VCO. What does VCO stand for? VCO stands for voltage controlled oscillator. That is a central piece of any analog synthesizer. Why? Well, because any music is, at the end of the day, just an oscillation at a certain frequency. So if you look at the top, okay, before that, if you check out the source for where I got the picture, it's anti-kpopfangirl.blogpost.com. Come on, like, you gotta appreciate that. Okay, okay. So any music is an oscillation, and oscillation of a certain frequency. So for example, a note A here has a frequency of 440 kilohertz. Oops. Note E 659, note B 123 hertz, and so on. I think I said 440 kilohertz. I meant 440 hertz. But basically, you need something that creates oscillation in order to produce music. In the world of musical instruments that are not electronic, so acoustic guitars produce oscillations using strings. In our analog synthesizer, we also need something that produces oscillations, and that is why we need a voltage-controlled oscillator. Notice the keyword controlled, and probably voltage controlled. Why? Because we don't need an oscillator that just produces random frequency. We need to know exactly what frequency we're producing, because that way we're making music. Otherwise, we're just making noise. And the way how the oscillations are controlled in analog synthesizers are with voltage, hence voltage controlled oscillator. Now, another important thing, note that, so look at this note A, this one, and this one at their corresponding frequencies. So 110, 220, noticing something? 440, 880. So on every octave, the frequency is doubling. So actually there is an exponential curve. It's the frequency is changing like this. Now, why I'm pointing this out? Why is it important in our design of the circuitry, or in this case, analysis of the circuitry? Because since we're controlling the oscillations with voltage, we need somewhere in our design, we need to be able to produce this exponential curve. That is something to keep in mind. Also, hold that thought and look at the analog synthesizer itself, and let's look at the knobs. So if you look at the knobs, they're actually linear. So this one here is, let me take a brighter color. This one, something smaller. This one here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Basically, the control knobs are linear. Why? Because for us as human species, it's just more intuitive to work with linear controls. We know exactly that 2 is between 1 and 3, exactly in the middle. 5 is exactly between 1 and 10, and so on. Probably 0 and 10. But you got the point. For people, it is more intuitive to work with linear systems. But to create music, we need to work in exponential system. That is why a heart of any VCO is a linear to exponential converter. So this thing in here. So if VCO is the heart of any analog synthesizer, then a linear to exponential converter is the heart of any VCO. Now, what does linear to exponential converter do? Well, it takes something that looks like this and converts it into something that looks like this. And how exactly does it do that? We will be learning in this tutorial. And I think it will be intuitive if we start with something that we can see on the panel. So for example, these two knobs here, let me take a brighter color. These two knobs are, well, actually not these two, but these 6. So 2 of these, and 2 of these are for frequency control. The reason why there are 3 pairs of them is because there are 3 VCOs in this synthesizer, so 3 voltage controlled oscillators. It just makes the sound of it more interesting. But we will only talk about one of them, and it has 2 knobs. Why? Because one of them is for coarse frequency adjustment and another is for fine frequency adjustment. So since they are knobs, they are connected to potentiometers, and they are shown right here. So one of them is for coarse frequency adjustment, another for fine frequency adjustment. And now let me redraw. I already redraw the circuit below. It's just easier to analyze it that way. So here we have a simple voltage divider where at the top there is plus 12, at the bottom there is minus 12 volts from the supplies. Then we have a 47, well, 49, oh, 50. Okay, well, I put it as 47K, it doesn't really matter. You have 47K on top, 10K on the bottom, and 100K potentiometer in between. So let's calculate the range for these for this potentiometer. We have 24 volt in total and 157 kilo ohm resistance in total in this branch. Oh, did I delete that? Yep, sorry about that. And we have so since all of these resistors can be split up into 10K resistors, I just find the voltage associated with each 10K resistance, and it is 1.5 volt. So that means if we start from minus 12, then 10k up will be corresponding to minus 10.5 volt. Then 100k up will be corresponding to plus 4.8 volt. So the range of I is from negative 10.5 volt to 4.8 volt. It will be actually a little lower than that, and I'll explain that later. So that is the range for coarse frequency adjustment, and this is the calculation for fine frequency adjustment. You have 200k resistor, 200k resistor on the bottom and on top, and between them 100k resistor. So we do the same kind of calculation, and we find that for every 100k resistance there is 4.8 volt drop. That means the range will be from minus 12 to minus 2.4, then from minus 2.4 to 2.4, and then from that to positive 12. So the range of values that the potentiometer in the fine tuning frequency adjustment can take is from negative 2.4 to positive 2.4 volts. Now, why is that important? Because the way they're connected to this summing amplifier. So this configuration right here, is a summing amplifier, and the output of this amplifier is related to is basically a sum of each of these inputs, where the ratio is given by RF, this feedback resistor, over resistance at the corresponding branches. So for V1 it'll be R1, for V2 it's going to be R2, for V3 it's going to be R3, and so on. Now, why is that important? Is because our coarse frequency adjustment is connected through a 100k resistor, and our fine frequency adjustment is connected through a 1 mega ohm resistance. Now, if you look at the formula, the bigger your resistor at that branch, the less will be the contribution of that specific voltage. So the new range for coarse adjustment and for fine adjustment will be not from negative 10 to positive 5, or from negative 2.5 to 2.5. It'll be from minus 9.6 to 210 millivolt, and then from minus 4.8 to 4.8 millivolt. You will find these values if you use the summing operational amplifier formula. Now, it's actually the range. The actual range is gonna be a little smaller than this. Why? Because if you look carefully at this diagram, then you will see that there will be some current that will be flowing from this node into here and into the op amp, and the same is gonna be with the fine frequency adjustment. So there will be some loss in there. And what is gonna be the exact range? Well, let's use multisim to simulate that part of the circuit. So let's take a look at this multisim simulation. This is the same part, so this is frequency adjustment part with coarse and fine frequency adjustment, as well as the summing amplifier part. And here we have our trimming potentiometer. So we can see that by varying the potentiometer states, so it can go from negative 9.6 to 3.4, so it's significantly smaller than our calculated range. Why? Because there is current. First of all, they are in parallel, and also there is current that is going into the feedback of this op amp. And the same is for this potentiometer as well. So it's going from 2.14 instead of 2.4 to negative 2.14. Now, notice that at the output of the op amp, we get, so let's change, let's take a look at this potentiometer and change it by 1 volt. So let's say right now it's 9.6 volt. Let's set it to 8.6. Also 9.6, and remember that here it's reading 196 millivolt. So let's change this to 8.6. Okay, so it's at 8.6 and the output is 176 millivolt. So you have 20 millivolt of change at the output per 1 volt of change at the front panel. And this trimming potentiometer here is to lower that ratio to 18 millivolt per 1 volt of change in there. So this is specifically here for tuning purposes. The requirement of having 18 millivolts per 1 volt of division is coming from our design requirement. It will be defining how many octaves our synthesizer can track. And after watching this tutorial, you're encouraged to find out why exactly it has to be 18 millivolt per 1 volt of division. But now let's go back to our slides. So you have these two inputs that are coming from fine and coarse frequency adjustment. But you can also have these so-called control voltage inputs. That is, you can attach some other, I don't know, waveform. So you can send a square wave in here. Let me do it differently. You can send a square wave into this port. You can send a sine wave into this port, and it will be, and these voltages will be adding up through this resistor, and it will be changing the voltage in here. So that is in there to create these unique sounding effects. You can experiment with that. If you add a bunch of different waveforms, you'll be creating very unique sounds. Now, that brings us back to the needs of this capacitor. So if you're sending, for example, a square wave into here, then the thing with square waves is that if this edge is going very fast from 0 to the top, so let's say from 0 to 5 volt very quickly, if this rising edge is sharp, then that means our voltage is changing very rapidly, and that will be creating magnetic fields around them. Those will be creating electric fields. Basically, you will have EM propagation caused by that. So you want that sharp change to be less sharp. You don't want to have sharp square waves in your systems. Why? Because those electromagnetic emissions, they are, well, some of them, first of all, might affect other electronics around you. So common case for the reason we have FDA is to not have a lot of electromagnetic pollution around us. Why? Because those can affect, there were cases where those affected some electronics in wheelchairs or some medical devices. So EM propagation is strictly regulated, and just as an electronics designer, you want to avoid having them. So that's reason number one. Reason number two, I'm not sure, but I think when you have a very sharp edge, it might have an unpleasant acoustic effect related with that. Um, and number 3, I wrote slew rate and crossed it out. Why? Because, well, any op amp has a slew rate associated with that. So, what is a slew rate? So the output of this potentiometer, it cannot go from 0 to, let's say, 5 volt very rapidly. There is a certain time it needs for that to happen. And for example, just due to the design of op amps, they cannot go like this. There has to be some kind of slope. I'm exaggerating the slope, of course, but this is needed to convey the point. And I crossed out the slew rate. Why? Because when you actually go ahead and calculate what slew rate you need for this case, so how do you do that? There is a formula that you need to use for that. It's 2 pi f times the voltage needed. If we're gonna input the numbers that we're gonna encounter in our application, then at output, we saw through our multi-sim simulations that we're never gonna cross a 0.2 volt threshold ever, and our maximum frequency is 20,000 hertz, and the calculated slew rate for that is 0.03 volt per microsecond, let's say that. And the op amp that we use, let's look at the circuit. Oops, wow, trippy. The op amp that we use is LF442. So if we open the datasheet for that, the slew rate that it can provide is 1 volt per microsecond, and we are well below the slew rate rating for this op amp. So in this specific case, that's why I don't think the slew rate was a consideration when Ray Wilson was putting that capacitor in there. So we can proceed with the analysis. Okay, so let's go. So what happens after we set our range for frequency adjustment? Then we have our linear to exponential converter, and I will actually go to this website. It's called schmitzbits.de expo tutorial, because this person already did an amazing job explaining that, and I'll be just going over it and commenting and providing more details if needed. Oops, sorry about that. Okay, so we're talking about linear to exponential converter. Here you can see that using a regular BJT, we can already get this exponential relationship. So if you change your V at the base, you get an exponential change in the current through the BJT. But there is a huge temperature dependence in the BJT, which you have to find out the way how you can circumvent that. And to kind of emphasize this relationship about the BJT performance and temperature, let's look at the formula. There are two temperature dependent relationships. Number one, this IS, this saturation current. If you look at the formula of how to derive it, let me find that. I think I prepared it here. Okay, so this current IS, the formula is given as such. So you have your cross section of the diode, you have elemental charge, you have Ni. Ni is number of carriers in an intrinsic carriers in this specific material. So for silicon, it will be a certain number, and so on. And important thing about this Ni is that in this specific formula, it is squared, and it's also a very high function of temperature. Now, it is a very high function of temperature, and it's also squared on top of that. How strong of a function of temperature that is, I prepared a datasheet about the properties of silicon. It's not a datasheet, but this website, yofe.ru, is a great database and reference for any semiconductor material, not only silicon. But here you can see the dependence of intrinsic carrier concentration on temperature. So if at 300 Kelvin it was, let's say, 10 to the power 9 carriers per centimeter cubed, at 100 degrees C it will be almost 100? Yeah, 100 times more. So it's 2 powers of 10 and so on, 2 or 3 powers of 10. So basically, it is a very strong power function of temperature, and it is squared. Now, what about the other term in the formula? So everything else, including the diffusion coefficient, the what is L? Diffusion length, and ND and NA are dopings for n-doped and p-doped regions of the diode, so they are not dependent on temperature, but dp and lp, dn and ln are temperature functions of temperature. But if you look here, it's actually square root of that dependence. So you plug in d in here, and you'll see that it's gonna be a very weak function of temperature. So the key parameter here is not this dependency, but this one. So if temperature in the room or temperature on the PCB changes, ever so slightly, it will have a significant effect on the on this BJT, and of course you will lose control over your frequency of the oscillation. So you need to find out a way how you can circumvent this temperature effect. Now, a very cool trick is to add a second BJT, and why that allows you to circumvent this thermal effect is let's derive the formula first. Okay, so we have that formula for first BJT, we have a formula for the second BJT, and and we have a current through it and also voltage at the base for both of them. Now let's solve these formulas for the voltages at the bases, and we will find the difference between them. Don't ask me why just yet. We will talk about this later. So VBE2 minus VBE1 is equal to delta VBE, which is equal to this formula. Notice something important. Your IS parameter disappeared. Why? Because you have logarithms, you subtract the two logarithms, and when you subtract logarithms, they cancel out. So you have IC1 over IC2 instead of having IC1 over IS and then having IC2 over IS. So now you solve this formula for IC2 like it's shown here, and you instead of calling IC1, you call it a reference current. So now you almost have an original formula, but instead of having a strongly temperature dependent IS, you now have a strictly controlled reference current, which is a great way to circumvent the thermal effect. Now you still have a temperature dependent coefficient in here, but as long as both the BJTs have the same temperature, this should not be a factor at all. And in our case, they are both in the same IC, in the same chip, so they are bound to have the same temperature. So this will be the same for both the transistors. So even though it will be causing some change, it will not be significant. It will not be too significant. Now, notice something interesting. You have delta VBE in here, and you also it's also an exponential term. So by linearly changing delta VBE, you will be exponentially changing IC2. So that is almost exactly what we want. Now we need to control the ratios of how much we need to change delta VBE and how much after that the current through the transistor will change. That is now if you remember that previously we had this requirement of having 18 millivolt per volt of division. Now everything slowly is gonna be coming into one whole picture. Okay, but that is all math, but how are you gonna implement that in the actual circuit? I've already redrawn the original circuit in here, so I'll show you what exactly did I do. So I've redrawn this this part of the circuit. This part we'll be discussing later. It's actually needed for this part, but for now let's focus on the linear to exponential converter. Okay, so I've redrawn it here. This is a very interesting circuit. So you see this I reference in here. The way you set it in this circuit is by using an op amp. So you have a virtual ground at this node. You have a 12 volt in here, and you also have a voltage divider, such that at the node right here, you get around, what is it? A little more than 6 volt. Let's say 6 volt for simplicity. You get 6 volt. You have 12 volt here. You have 6 volt here. That means you have a 6 volt drop across a 1 mega ohm resistor, which gives you around 6 microamp of reference current. And again, this is set by your resistor and op amp, and this shouldn't change much. With temperature. Now, what happens next? You set your reference current. Now remember that op amp will be, the output of the op amp will be doing everything to keep that current constant, because current can't go in into the op amp through the terminal. Oops, why is it minus? It can't go into the op amp through the inverting terminal, so it has to go through here. So the op amp will be trying to sustain that, and in this case it will be doing that by sinking current. How exactly does it do that? So if you look at the original formula, again, let me clean this up. So let's look at this formula. You have I reference that you already set, and you have a delta VBE that you control. This delta VBE, you have a specific range for that, and that range we saw from the multisim simulation is from 71 millivolt to around 196 millivolt. This is, by the way, my MATLAB simulation of the linear to exponential converter. So we have our V-in, which is voltage, input voltage, which is coming from our coarse and fine frequency adjustment, which is coming from our summing op amp. Then we have a reference current that we set using our op amp. Then we have this Q. This is Q over KT factor, which is from here. I just set it as a constant. So you can see it's a constant. And then we have a formula for I out. So I just took this formula and plugged it in. I put it into MATLAB and then plotted input voltage and output current. And if you look at the curve, this is exactly what we wanted to achieve. So we have a linear change in voltage. So this is V in. And we have a exponential change in current. And the shape is exactly what we wanted. Oh, did I delete that? Okay, that's fine. So what do we do with this information? Well, first things first, let's look at this region. Since this is an exponential function, it will keep increasing, and it might reach 1 amp like very soon, maybe next 0.1 volt it will be already at 1 amp. So how do we limit current? Well, the current limiting is achieved with this resistor. So since this BJT will be conducting current based on the VBE applied in here, our what is it called? This terminal will be 0.7 volts lower than V base, so it will be minus 0.7 volt. And the in order for the op amp to sink current, the maximum voltage that it can get out the output is one of the rail voltages. So let's assume it's minus 11.7 volt for simplicity. It's probably going to be less than that, but for simplicity, let's assume it's that. Then you will have minus 11 volts drop over 10k resistor. And I'm reminding you that we're taking minus 11 volt because that's the maximum voltage that the op amp can provide at the output, because it will hit one of the rails, so a negative rail in this case. So you will get maximum of well, it's minus 11, so it's actually 11 volt positive drop across this resistor. Is it? What am I doing? Yeah, it's positive. So from this terminal to here, because current is flowing in this direction. So the maximum current that'll be flowing through that resistor is, in this case, 1.1 milliamp. And that is the purpose of this resistor. Now look, if this resistor was smaller, then there will be 1.1 volt flowing through, 1.1 amp flowing through it. Or if this resistor was larger, so let's say not 10k but 110k, it'll be 0.1 milliamp flowing through this transistor. But we set the limit at 1.1 milliamp. And that 1.1 milliamp will be flowing into this terminal. I know it says output, but it is the effect is just negative current that is flowing into the circuit. That will be I assume output in this case. So, and as a result, by linearly changing our delta VBE, I remind you we're changing this with coarse and fine frequency adjustment through summing amplifier. By linearly changing that, we are exponentially changing IC2, and here is the shape of the relationship between V in I out that we're achieving. And IC2 is in here. And let's look at the circuit. Let's look at the original circuit and how it looks in there. So we have IC2, which is in here. So this is IC2. And where is it connected? It is connected to this terminal. So this brings us to a ramp oscillator, which is this part. Before we go there, I realized I forgot something. It is this linear CV input. Let me make a quick comment about that. I actually I actually put it here, but didn't comment on that. So if you look again at the formula, by linearly changing delta VB, you'll be exponentially changing. Oh, my battery's dying. IC2, but if you change I reference, then you'll be linearly, okay, by linearly changing I reference, you'll be linearly changing IC2. So you can linearly change I reference if you apply a CV voltage at this terminal. So you apply some voltage here, then voltage here changes, then current through this resistor changes. That means I reference changes. This is again done to achieve very interesting sound effects in your analog synthesizer. Now let's talk about the ramp oscillator. Well, ramp oscillator is very simple. It consists of an op amp and capacitor at the feedback, and also this reset transistor. Now let's talk about its working principle in more detail. Well, you see, this is the formula of current through a capacitor. And by the way, this current is our friend from here. It's IC2. So in order to avoid confusion, oops, what is this? I will specify that it's IC2. So we have control over this current. So let's assume that for a set frequency, so we are playing our analog synthesizer. We're turning the knobs. We turn the knobs and we set it there, and we don't touch it. So that means our IC2 is constant, and we are constantly drawing current from this terminal. And this transistor is here is MPF 102, which is a do I have a data sheet open for that? Let me double check. Yes, it's NPF 102, which is N-channel depletion mode JFET. Depletion mode means that it's normally on, but in our case, let's say that it is right now off. There is a reason for that. We'll talk about this later in the analysis, but we assume that it is normally off, and it will be turning on at a certain condition. And again, everything I'll be explaining later. So this IC2 current is being drawn through this terminal, and it is not coming from this node. Why? Because op amp, no current goes into or out of the non-inverting or inverting terminal of an op amp. So no current is coming from here. That means all the current is coming from this capacitor. That is why we need this formula. I is equal to C over the rate of change of voltage across the capacitor. Now, in order to find voltage, since this node is virtually tied to ground, so there is a virtual ground in there, this terminal's voltage has to rise from 0 to to V plus upwards, and we'll be so it'll be looking like this, and we'll try to find this slope of the rate of change. So how do we do that? Having this formula, we solve it for V, and here we have I over C. We put dt into this side, we multiply both sides by dt, then we take integral of that. Since I and C are constants, we can write it like this. Now, here's something interesting that happens. The maximum that this capacitor will ever reach will be set at 2.2 volts. Why? Because these okay, let me look at the original circuit, I'll tell you why. So the entirety of this circuit is doing one simple thing. It says when VC7, so voltage across this capacitor, reaches 2.2, then reset the JFET. So when VC7 is at 2.2 volts, then this JFET will be turned on, and the capacitor will discharge and go back to 0. So, and I'll explain you how that part of the circuit works as well. But for now, this is how the operation of that, how the voltage change across that capacitor looks like. So at this terminal, it will be going from 0 and rising at a certain slope, which is defined by I over C. It will reach 2.2 volts in here and reset to 0. Then go up again and then reset to 0 and up and so on. Now, if we know this reset voltage, that means we can state the following. So integral of dV, we know that V is just a constant, so it'll be just 2.2 volts. So that means we have a constant dV equal to I and C are constants as well. C is just the capacitance of the capacitor. I, we tuned our frequency and we left it there. That means I is constant as well. That means we can find the period of this waveform. If we know the period, 1 over period will be frequency. And tada! By controlling our voltage using our knobs on the front panel, we first reduced that to a ratio of 18 millivolt per volt of changing on the front panel. Then using that, we converted linear changes in voltage into exponential changes in current. Using that current, we set a certain frequency for our oscillation. In this case, this ramp waveform. And I think yes, I actually plotted the performance of this or input to output relationship of this waveform. So this all should be familiar. This is from previous code. We have I reference, we have V in, we have Q over KT, we have our current output, which is I2. Then instead of plotting V in over V in and I out, I calculated the frequency, which is coming from these two formulas. I calculated the frequency and plotted the semi-log plot. So here you can see that this is so important that I'll be probably just writing it down. So linear change in voltage leads to exponential change in frequency. You can see that the scale here is linear and that the scale here is exponential. And here you can actually find what node corresponds to a what control voltage. So if we need node A, which is 440 hertz, let's try to find it. So we have 100, 200, 300, 400. So 440 will be around 0. Around 0 volt will be our node A. So it's pretty cool. Okay, so how does this reset circuit work? So how does this part work? How come that we can set the such an interesting condition that when VC7 is 2.2, then reset JFET? Well, it is done in the following manner. So this is our familiar ramp oscillator. And now take a look at this circuit. So this circuit in here is a Schmidt trigger. What does that mean? It is a... Well, let me go through it very slowly. Yeah, so this is a circuit of the Schmidt trigger in the original analog synth circuit. You will notice here that the analog synth also has a 4.7 picofarad capacitor, but it's the same thing as we discussed previously. It's to reduce EMI and probably has to do with the slew rate of this specific op amp. So we can ignore that safely for now and just analyze the Schmidt trigger. Domino's Pizza is sending me email. Okay. What was I talking about? Yes, Schmidt trigger is... Let's analyze the Schmidt trigger. Notice that the feedback is connected to a non-inverting terminal. That means that the feedback will be positive. So positive feedback. Positive feedback means that VO can only exist in two states. So it's plus and minus rail voltages. In our case, it'll be it's connected to 12 volt, but it's actually gonna be probably like 11 and a half, let's say 11 and a half volts. This has very interesting implications. Why? We will solve it. We'll derive a little below. So we have a reference voltage of 2 volt. This is, by the way, what sets our threshold for the when the JFET needs to be reset. So we have 2 volts here. That means we have virtual 2 volts here as well. So that's why the current that is flowing in this direction, let's say, will be the same as current that is flowing in this direction. So 2 minus V in over 10K is equal to VO over minus 2 over 1 mega ohm resistor. We solve this for V in, and we see that since VO can only be plus minus 12 volt, well 11 and a half we said in this case, then this can be, so let me plug it in. What is it gonna? So this was 1.9, and we can actually plot that here. So initially current is output voltage is at minus 11.5 volt. Why? Because it's less than this upper trip voltage. It's less than that, so it's at the negative rail. Then when it hits that threshold, it shoots up to the positive rail of 11.5. Then when it goes back, it needs to reach this negative trip voltage, and which is 1.9, which is slightly less than 2. It will go back and so on. So this is a typical Schmidt trigger. Now, what happens when it's at either of those states, when it's at minus 11.5 and 11.5? So notice that this V in is our ramp voltage. So our ramp voltage, this one, it starts from 0. So starts from 0 and ends, we'll see when it, and let's say it starts at 0 and rises. So it starts at 0 and it rises. So it is at this point, and then it goes like this. It reaches 2.14 or 2.2, and it shoots up to 11.5. So initially the ramp voltage is at negative 11.5. So now look at this part of the circuit. This part. What happens, and I've redrawn it here. So what happens at this part of the circuit? So initially at negative 11.5. So this is negative 11.5. Here you have negative 12 volt. So at this node you have negative 12. And this diode is, which one is that? This is a regular 914 diode, and the forward bias voltage for this is around 1 volt if you look at the datasheet. So there is not enough of voltage drop across this diode to forward bias it. So this diode is not conducting, and I guess in this case it's not important, but the point is at this node you have negative voltage. So at this terminal of JFET you have negative voltage, negative 12 volts in this case. And since this is a n-channel JFET, when you apply negative 12 volt at the gate of the JFET, then your JFET is depleted. It's not conducting, so it is off. So you see that by default your JFET is off. That is why we had that assumption before. Now what happens when the V in starts to rise? So it's at 0 and it starts rising, we already said earlier. So it rises, it reaches 2.2, and then it shoots up to 11.5 volts. So it goes from here, it becomes 11.5. So now we have a significant drop across this diode. So that means there will be, this diode is conducting, and then since this diode is conducting, there will be a point or like 1 volt drop across that diode. That means at this node we will have 10.5 volt. We have 10.5 volt here. That means our JFET is on. And when our JFET is on, what happens is that, let me clean up this mess a little bit. What happens when this JFET is on? Your capacitor starts to discharge. So the voltage at this node is equal to the voltage at this node, and the voltage at this node is equal to the voltage at this node, which is ground. So voltage at this node resets to 0. So this transition happens. And that is pretty much how your voltage controlled oscillator works. And I prepared a celebratory slide at the end. Congratulations, you created an oscillation with a controlled frequency, which is music. Whew, great job, great job. In the future, so for now, we only talked about these parts of the circuit. So we talked about the frequency adjustment and summing. We talked about linear to exponential converter, and also about the creating oscillations with the controlled frequency. Later, we will be talking about wave shaping. So we'll be talking about how to create this sawtooth wave, how to create this pulse wave, well, I guess square wave and PWM. Oh, no, wait. Oh, yeah, this one doesn't have PWM. So we'll be talking about wave shaping. And also, this is only one page out of many. There are actually, let me see. So you have VCO1, which we just analyzed. There is VCO2, VCO3. There is audio mixer. There is noise generator. There is, what is it? 2-pole voltage controlled low pass filter. So you get the point. There's a lot of material in here, and I encourage you to go through it on your own, applying the same strategies, the same principles that you learned in this video in your electronics classes, from your own experience. Analyze the circuits, post some tutorials online on YouTube, and next time I'll be watching your tutorials. And yeah, thank you for watching.